So in this lecture series, we'll learn about the Lagrangian formulation. So remember, the Lagrangian of a system is written as L. L means the Lagrangian of a system. Now what is Lagrangian of a system, that we'll see. But first consider two systems. Now system number one is an object falling under gravity. We have already studied this system in our last class. So when an object falls under gravity, so consider this side, we have the x-axis. So what are the two energies when an object falls under gravity? It has two energies. One is the kinetic energy, that is given as half into mass of the object falling into velocity of the object at any instant. If the object is at a distance x from the ground, then what is the so this is the kinetic energy. So if an object is at a distance x from the ground, then what is the potential energy? The potential energy is given as, you know it very well, that is m into g into x. Okay. Similarly, consider a second system. In second system, we studied about a spring mass system. Okay, that you have done already in our last class. So what you have to do, consider a spring connected to a particular mass. In this system, what was the kinetic energy we discussed in our last class? The kinetic energy is always half into mass of the system into velocity of the system square. But potential energy will be different. Remember, what is the potential energy? Potential energy, if the object was at equilibrium at x equals to 0, and if it is stretched by a distance x or compressed by a distance x, then the potential energy is, in case of spring mass system, is half k into distance of compression or expansion, so whatever you say, or stretching square. So x is whether you have compressed or you stretch it. If you push the mass towards the right by distance x, you stretch the spring. If you push the object left to by distance x, you compress it. In any case, potential energy will be stored. Lagrangian says that define something called as the Lagrangian, which is the kinetic energy minus the potential energy. See, kinetic energy is sometimes represented as T in many books. Before that, let me tell you that velocity is what? Velocity is dx by dt. You all know velocity is rate of change of position. In many books, they write, instead of writing dx by dt, they make it x dot. Why they make it x dot? Because it makes life simple. You don't have to write again and again dx by dt. So just write x dot and things are understood. So the Lagrangian says do t minus v and then use this in a particular formula called as the Lagrangian equation of motion, and that formula is, you have to do derivative of time derivative of the partial derivative of the Lagrangian with respect to velocity. What is velocity? Velocity is x dot. So let me write x dot instead of velocity, minus you need to do partial differentiation of Lagrangian with respect to the position, that is del x, and equate it to 0. This is called as the Lagrangian equation of motion. So one, we define the Lagrangian, and second, we define the Lagrangian equation of motion. So let us see what happens in case number 1 when we apply the Lagrangian equation of motion. So what is the Lagrangian in case number 1? The Lagrangian in case number 1 is kinetic energy, that is half into m into v square, minus the potential energy. What is the potential energy? M into g into x. Remember, this is Lagrangian equation of motion in one dimension, and we have considered both the cases which are 1D cases. Now let us put it in the equation. So can you tell me what is del L by del x dot? See, as I mentioned earlier, x dot means velocity. So you can write del L by del V. Now can you tell me what will be the answer? If I differentiate it, the only term that will get differentiated is here. This will not get differentiated and will fetch me a 0. So the answer will be m into v. Agreed? It's very easy. Then second step is you have to do d by dt of del L by del x dot. So what is del L by del x dot? We calculated it is mv in this case. So write d by dt of mv. Now m is constant, will come out. It dv by dt is acceleration. So you get m into a, acceleration. Agreed? Then we have to solve del L by del x. Okay. So what is del L by del x? So you have to do d by dx of the complete L. So what is L? L is composed of half m v square plus minus m g x. Now tell me which is a function of x. Only this is a function of x, so no derivative here. This will fetch me a 0. So what is the answer? The answer is minus mg after the derivative. Now apply the Lagrangian equation of motion. So what is the first term? The first term we get is ma. So what is this term? This term is now in our case ma minus, what is this term? Del L by del x. In our 1D object when it was falling down, it is it is minus mg. So minus mg equals to 0. Okay. So now what you find is, for a moment, you see one thing. If you just apply ma and take it to the other side, you get what? You get minus mg. For a moment, just apply mod. I don't want to consider the minus sign. For a moment, if you apply the mod, then what do you get? What is ma? Ma is the force equals to, and this side we have mg. What is F equals to mg? Whenever you see F equals to mg, you know that an object is falling under gravity, because only this force makes objects fall under gravity. It means that if you somehow know the energy of a system, I mean, if you somehow know the energies of a system, both the kinetic and potential energies, then Lagrangian equation of motion will exactly tell you what are the forces acting on the system. Quite interesting, right? Once you know the energy of the system, define a Lagrangian, put it in Lagrangian equation of motion, and the Lagrangian equation of motion will fetch you the value of the force or the expression of force that acts on the system. So Lagrangian equation of motion says that in case 1, the force under which the system is moving is F is equals to mg. Okay? Okay. Now let us consider the second equation and let us solve everything for the second equation. So we don't have space, and let us do this side. Yeah, we'll do this side. So for the second equation, so you know kinetic energy is half mv square. So what will be the value of d by dt of del by del x dot of Lagrangian? Okay, so what is the Lagrangian? In spring case, the value of Lagrangian is t minus v, that is half m v square minus half k x square. So what will be the value of this? Since only the first term is the expression that depends on velocity, and this is what x dot means, as I said earlier, it's velocity. So you get d by dt of, obviously again you will get mv, and that will give you m into dv by dt into acceleration. Now what is the second term? Second term is del L by del x. So if you do del L by del X, then obviously it will act on this, not on this, because it's not a function of x. Only half kx square is a function of x, and the answer is kx. Now what you need to do? Now you need to write the Lagrangian equation of motion. This is the Lagrangian equation of motion, and then put all the values. So what is the first value? The first value in this spring case is mass into acceleration, and minus of, what is the second value? Second is minus kx. So what is mass into so this is equals to 0. So what do you get? What is mass into acceleration? Mass into acceleration is my force, and when it comes to this side you get minus kx. Quite amazing, right? So this also does the same thing. Once you know the energy of a system, so we know the kinetic and potential energy of a spring mass system, and the Lagrangian equation of motion happily gave us the force that causes the spring mass system. I mean the force that is responsible for simple harmonic oscillation. So here, by giving the information of half mv square and half kx square, I told the Lagrangian, hey look, I am using the simple harmonic oscillation. Then the Lagrangian said, okay, let me find the force that is working in your simple harmonic oscillation. So how the Lagrangian found out? The Lagrangian finds the force by putting it in the Lagrangian equation of motion. Amazingly, we get F equals to minus kx. Okay, are you convinced? No? Okay, let us see one more example. In the third example, we will consider a, so I'm rubbing the first example. So in the third example, we'll consider a object, a free object. Okay. So can you tell me, if a ball is moving at a velocity v, then what is the force acting? Remember, we already discussed, if an object moves at a constant velocity, the force equation is 0. Let us see if the Lagrangian says the same thing. Okay. So the Lagrangian says that you have to subtract the kinetic energy minus the potential energy. So what is the kinetic energy of a free object moving at a particular velocity? It is half into m into v square. Now what is the velocity? What is the potential? The potential is 0 because no force or potential is acting. So a free object, a freely moving object only has kinetic energy. Now the Lagrangian says, okay, so what is the Lagrangian now? The Lagrangian is t minus v. Since v is 0, so the Lagrangian is only half m v square. Now the Lagrangian says, put me into this equation of motion. So that is d by dt of del L by del V. V is velocity, or I should write x dot, minus del L by del x equals to 0. So if I do del L by del x, what is the answer? It's 0 because there is no term in the Lagrangian of the free body that moves with that is a function of x. And if I do this part, already we have done this again and again, what do we get? We get mass into acceleration. So mass into acceleration minus 0 equals to 0. And so what is mass into acceleration? Force, and everything is 0. So force equals to 0. Yep. So Lagrangian equation of motion said that if an object only has a kinetic energy, it means it has a constant velocity, and if an object has constant velocity, the Lagrangian says that the force acting on the object is 0. So once we gave the information of the energy of the system, and we fed it into the Lagrangian equation of motion, the Lagrangian equation of motion gave us the idea or the information of what are the responsible forces. Of course, in a free body there is no force, so this is the case. So force is 0. This is quite amazing, right? As if we have found out a formulation that connects the energies with the forces directly. It is quite an amazing formulation that makes our life hell lot of easier. Now we can consider any complicated situation. If I give you one complicated situation where there is a sun and there is a earth, the earth is moving around the sun, and I ask you what is the force, it's quite hectic. But Once you know that this earth will have a potential energy, that you know, that is a gravitational potential energy, this earth will have a kinetic energy, and then you put this information in the Lagrangian, and the Lagrangian will tell us what is the force that causes the motion of earth under the sun. Agreed? So there are many complicated situations. If I ask you a spring mass system, so a mass is connected with two spring, and you are asked what is the force responsible in this case. If you don't know, then just make an idea of the total energy of this system, put it in Lagrangian equation of motion, and this Lagrangian equation of motion will exactly tell you what forces are acting under this system. In many cases, there are many complicated systems. So I have discussed only three systems that you already know to show you the power of Lagrangian equation of motion. But there are many complicated equation of motion, complicated systems whose equation of motion is difficult to find, but their energies are difficult to evaluate. In those cases, we can use Lagrangian equation of motion to find the responsible forces. Okay. So this is, we discussed the Lagrangian is in 1D, as I've stated earlier. All the equation are done in one dimension because I have taken only one variable, that is your x. But now in the next lecture we'll do 2D case and more 3D.